Okay.
Okay, Mark, have at it.
All right. All right. Can you see my presentation?
Yes.
Okay. Oops.
Yeah.
Hang on. It's going on the wrong screen for some reason. Okay. Well, I'll just do it full screen like that. I wanted to start off by saying I really love this group here, and the meetings and the forum, because you guys have got so much experience, and I've learned so much from participating in this. I really want to thank you all for helping out, probably more than you think you do. Let's see. This presentation is about using a big dual band filter with a color camera. Josiah and I have been imaging for, well, since December with the refractor down in Dark Sky, New Mexico, using a color camera with a dual band filter for some of our images. And there was a thread, I think I heard about it first from this group's forum. There was a thread on cloudy nights about coming up with a way to actually create pure hydrogen alpha and oxygen 3 images from using that dual band filter. And so that's kind of what the presentation is about. So when you're using a color camera and a dual band filter, anytime you're using a color camera, really, there's really 2 filters that are in your image train. Whatever filter you're using, in this case, we're going to talk about using the dual band filter and the Bayer matrix that's in the camera. The Bayer matrix has transmission curves in it for the red, green, and blue filters that are in front of the pixels. And those red, green, and blue filters for the pixels are actually pretty wide, and they tail off into some of the other colors. And so any image you take, some of the red photons, some of the blue photons that come in can get leaked into the red channel and vice versa for all 3 images, or all 3 colors. So here's just an example. This line here is the red pass band for the Sony color camera Bayer matrix. Okay, so all the red pixels in the camera have this pass band. That's the photons they'll let through. And with a dual band filter, you've got signal at 656 nanometers, which is in the red band, which is your hydrogen alpha, and you've got photons from the oxygen 3 band, which is at 500 nanometers. And you can see that the response curve for the red Bayer matrix is not 0 out here. So some of those O3 photons are going to end up in your red channel, and vice versa for the green channel and the blue channel with both HA and red and O3. Okay, those pass bands for green and for blue don't eliminate HA from green and blue, because there's a non-zero response down in here for those. So when you put those 2 together, the resulting flux into your red pixels looks like this. Most of the flux in your red pixels is from the hydrogen alpha, but there's a little bit of leakage into the red pixels from O3 emission. And vice versa, if you look at the green flux, again, most of the flux that goes into the green pixels is from 03, but the response curve of the green filter down here at the HA wavelength is actually pretty high. It's almost like, 17 or 18% of the HA pixels could get through into the green channel of the color camera. So this, I kind of thought about that for a while, and I thought, is there a way to create more of a pure HA image and O3 image by doing some sort of mathematical operation on the red and green pixels? I chose the red and green because obviously for the HA you want red. Green, the O3 is actually kind of in between green and blue, but the signal for O3 is typically stronger in green than it is in blue, so I figured that was a better choice. I really didn't need all three colors in order to solve the problem. So the things we're going to talk about here are the filter transmission curves, determining the flux based on the transmission curves, solving the equation, and finally creating the HA and O3 images. This presentation is just going to be about what the numbers, at least in this presentation, are going to be based on our combination that we're using. We've got Optilon L Ultimate dual band filter that has 3 nanometer bands at 500 and 656 nanometers, and ASI 2600 MC Pro camera, which is a APS-C camera with the Sony IMX 517 sensor and the Sony RGB Bayer matrix. To get the filter transmission curves in PixInsight, there's a process called spectrophotometric color calibration, which I will refer to as SPCC from now on. And there's data files you can get out of that have transmission curves for the various filters and filter combinations. And to get to those, in PixInsight, you open the spectrophotometric color calibration process, and there's a button there called Filter Management. When you press that, this window pops up, and you can export those filter definitions into a CSV file. And so that's what I did. And what's in those CSV files? It's got some header information, but then the data it's got is transmission values from 0 to 1 for integer wavelengths for these filters from 495 nanometers up to 666 nanometers. All of the transmission curves for whatever filter you're looking at from those CSV files only include whatever the range of wavelengths there are where the transmission is non-zero. And if you go into SPCC and want to see the curves and the files that I used, these are the two that I used, was the Sony CMOS R combined with the Optilon L Ultimate and the Sony CMOS G combined with the Optilon L Ultimate. And if you want to see what those look like, this is actually one of those CSV files. These 4 rows are the actual contents of the CSV file. I just took the wavelength and transmission values and flopped them over so I can make a table out of them. And that's what SPCC uses, and that's what is in that CSV file. So it's got integer values for wavelengths and then a number representing the transmission. Now, this transmission value here is a combination of the filter and the Bayer matrix. So it's got both of those built into it. And so that's there's a similar table for the green. That one was the red one. So to get the transmission values for each passband, I just summed up what the transmission values were for each of the wavelengths in those pass bands, and ended up getting 4 values out of that. The percentage of hydrogen alpha and O3 signals that go into the red channel, and the percentage of hydrogen alpha and O3 signals that go into the green channel. And if you look at it in here, I've got this little area here called total flux. And all this is this value is the total flux in HA. It's just the sum of the transmission values for the HA pass band for the red pixels with that filter. And then the O3 is just similarly the sum of all those values. For those of you who are mathematically inclined, that's called numerical integration, adding up flux values. That was a joke, a little bit of a joke, very little bit of a joke, I guess. So having those numbers, you can come up with a couple of equations that say, you know, for incoming HA and O3 photons, what's your red signal going to be based on the given values of HA and O3, and what's your green pixel value going to be for a given set of HA and O3, where the A, B, C, and D are the percentages that are derived from the transmission curves. Red, green, HA, and O3 are signal values or photons, whatever you want to call it. For signal values, they would be an ADU, and this is on a per pixel basis. And when you've got your image taken, your red and your green pixel values are your knowns, and what you're trying to solve for is the HA and O3 values, which are the unknowns. So you have to take that set of equations and flip them over so that instead of having red and green here on this side, which is what we can determine from the transmission values, convert it into a set of equations that'll tell you what the HA and O3 values are. If any of you guys go back to your high school algebra, you can actually solve those equations algebraically using standard substitution principles. I asked the guys in my SIG, for my local astronomical group, whether any of them thought they could do that, and none of them said yes. It's actually easier to use matrix math, which sounds way more complicated, but it's actually much simpler. All you have to do is invert the matrix of the coefficients, which is the A, B, C, and D values, and it'll give you the answers for the A prime, B prime, C prime, and D prime values. And I do that again in the spreadsheet. So based on those integrated flux values, which I get from these two tables, from the red and green transmission curves, I calculate, you know, what percentage of HA goes into red and green, what percentage of O3 goes into red and green, and that gives me the A, B, C, D values for that first set of equations. And to reverse it, this is what the matrix version of it looks like. And I did a little text box down here to show you what it looks like. This is what those equations look like in matrix form. The solution to those is really pretty easy. All you do is you divide both sides of that equation by the matrix of the coefficients, and you end up with the inverse of the matrix of the coefficients times the red and green values to get your HA and O3. So I didn't do that by hand. There's a nice little function in Excel called M inverse. And all you got to do is just point that at your matrix and it'll tell you what the inverse of the matrix is. I did do it over here kind of by hand just to make sure I was getting the same answer. and it gives you this equation. So this is the equation using the data for my filter and my camera for how to reproduce HA and O3 given red and green pixel values for each pixel. Okay, so that's the solution to that set of equations. If you guys wanted to do this yourself with, let's say, a different camera or a different filter, all you would need to do is use the same spreadsheet, and I'll make this available to everybody, and fill in this data. What is the transmission value? What are the transmission values at every wavelength for HA and O3 in the red and in the green? And the SPCC is one place you can go to look for that. It has other filter combinations in it, like for L enhance and an L extreme, I think, are two other dual band filters that Optolong sells. So I took these equations, created a pixel math script in PixInsight to create HA and O3 images from those equations. Pixel math process that I created puts the resulting HA values in the red channel and the resulting O3 values in both the green and the blue channel. So it basically creates an HOO image from the original RGB. When I do this after running Star Exterminator. So I only do it on the nebulosity in each image. I don't do it on the stars. When we do final images using the dual band filter, we also have another, I call it a clear filter. It's really just a luminance filter that does a normal RGB. We always take regular RGB images along with the dual band, and at least we use the stars from the RGB images in our final images. So we usually don't use the stars from the dual band images just because without any true blue emissions going into them, the stars always look funky with dual band. Any of you guys have used a dual band filter with the color camera probably know that your stars always have funky colors on them. That HOO image that I create can be color separated, and you can use the red channel for HA and the green or the blue. They're both the same for O3. And again, I'll provide that pixel math script that incorporates the values for my filter and camera combination as the part of the information from this. There's an issue of clipping. If you look at those formulas, you're multiplying by numbers that are greater or less than 1, or greater than 1 and less than 0. In PixInsight, internally, it uses 32-bit floating point values for all of your pixel values. All the values are between 0 and 1. So no matter what your camera is doing, usually 14 or 16-bit integers, in PixInsight, it converts those all into floating point numbers between 0 and 1 with using whatever the maximum value that you can have for a pixel in integer as being 1. So anyhow, to avoid clipping at the high end, you want to kind of make sure that this number or this number won't cause whatever your pixel value is to be greater than 1. Even if there's no, let's say you've got a pixel that's got a lot of red and no green in it, or a pixel that's got a lot of green and no red in it, you wouldn't want those to be greater than 1. So to avoid that, your pixel values really shouldn't be greater than about 95% red, 85% for green, and your RGB image when you start. Typically, that's not an issue. You would never really stretch your your starless RGB image or your starless dual band image to higher than 90, 85% or something like that anyhow. Clipping at the low end, I don't think is an issue, again, because these formulas have negative numbers in them. If you had a pixel that had very little red and some green in it, you might get a negative number, or vice versa. But notice that if it didn't have much red in it and had a little bit of green in it, that's an indication you didn't have any HA there anyhow, so it's not an issue that it clips it to 0, and vice versa here. So I don't think clipping at the low end is really an issue. It basically means that the background signal, there's other photons that can get into the HA and O3 bands that don't come from hydrogen or oxygen emission, and so if those numbers are a lot higher than the emission signal, just means there's little or no emission signal in a pixel anyhow, so I wouldn't worry about it. Pixel math does, because of the way PixInsight handles images, truncates any pixel values that are greater than 1 or less than 0 before it puts it into the image. So what's the results or the considerations for this? The main benefit for this is in O3. In my example, we subtract, actually it should be 19% of the red signal from green to give the O3 signal. So using just the original green for O3 made it hard to highlight O3 areas, I thought, because of the large amount of HA that ends up leaking into the green. And that shows up in those transmission curves for that filter. Another thing to consider, this procedure assumes that the only flux that comes in the HA and O3 path bands is just from pure HA and O3 emissions. But we know that's not true. There's other sources of photons at those wavelengths that can come from sky background, from thermal sources like stars, or from reflections of thermal sources. But that's true for any bandpass filter. Even if you're using a mono camera, your HA images with a HA filter in a mono camera don't include just sources or photons from hydrogen atoms that are glowing. It comes from stars and from other things too. So the result is not exactly the same as you would get from using individual HA and O3 filters. How much does this affect the result? The background signal is generally going to be much smaller than your HA and O3 signals in areas where you have some nebulosity. And even if it was 10 or 20% of the HA or O3 signal, the difference is going to be very small. It's going to be like 10 or 20%. I don't know why I put 17 in all this here. It's going to be 10 or 20% of the 5 or 19% that you're subtracting out, which means it's really going to be less than, it's going to be 3% or less of the final value, 3 or 4%. If the background signal is like 50% of what your HA or O3 emission is, the difference that you get in the result is larger, but it's just in areas where the HA and O3 is pretty weak. If your HA and O3 signal is no higher than twice as high as the background, it's going to be pretty weak anyhow. So I just wanted to give you some. You see my PixInsight screen now? Everybody, can everybody see that PixInsight screen?
Yes.
Pardon?
Yes.
No, yeah, okay. Okay, so this is what my M8 dual band starless looks like without any correction and just taking the straight dual band. This is what it looks like when I do after I do the correction. So that's the original, that's the corrected version. So it makes a big difference. And I guess it's kind of from an artistic span. Some people might think that looks better than that, which I can't argue too much with. But this version here is a lot easier to work with because the O3 ends up being more isolated in areas where there's really O3. Interestingly, I did another example of it. Let me just show you the issue that came up with, and I kind of came up with this today, so it's kind of new in my head, was when do you do your color correction, color calibration on these images? You know, and color image looks awful until you do color calibration on it, because the Bayer matrix pattern is RGGB. So there's basically twice as many green pixels as there are red and blue pixels in each color image. You know, your standard Canon or Nikon DSLR corrects for that internally in the camera, but your Astro cameras don't. So I did it two ways. I did it by, the way I showed you before was doing the correction after I did the color calibration. And this is an example of doing the correction, the pixel math corrections, and then doing a color calibration on it. And so that's doing color calibration first. That's doing the HAO3 conversion first. I actually think that one looks better. And I haven't gotten to the point where I actually tried to use that, but you can actually see a little bit of the blue and green here. And this is M8 and M21. You can see a little blue and green over here in the Trifid Nebula that you can't see in any of the other versions of that. And just real quick, I'll show you the pixel math. This is the pixel math script that process that I write. And I put my two coefficients in here. And this is basically the formula for the HA. And in the green and in the blue, I've got the same formula, which is the formula for the O3. So when I run that on a unconverted image, it generates a single image, an HOO image. By the way, these images always look a lot better with stars in them. Let me put the stars in them. What? So again, that one is the image where I did the HAO3 conversion first. And that's the image where I did the color calibration first. Again, I kind of like that one a little bit better, but you can see there is a difference, a pretty big difference in some cases. The only one I've really worked extensively on with is this M8, M21, M8, M8, M20 image. So that's it for my presentation. Questions or comments from anybody? Okay, well, the files, the presentation, the spreadsheet, the pixel math process icon will all be available. I'll send them to Dan or post them on the forum.
Yeah, if you can send them to me at some point, I'll post them in the file section.
So Mark, this is Dave Wood. I thought was like really instructive, and I kind of agree with your assessment of the two choices there in order of oil calibration. The
Thank
one you
you.
like better look sharper to me, at least on my screen. Looks a little more detailed somehow.
It's not going to be a huge difference. I mean, you're making 5% correction or 20% correction, depending on which color it is. But it almost depends on what can you do with it after you get done doing that conversion. I don't know. I have a degree in physics, and I spent 30 years as an engineer at Boeing, and I just want things to be correct, not necessarily artistic.
Well, aesthetically, that I'm lining up with you. Whatever the math is says.
Yeah. And like I said, it's really not that hard to do. You just need those 4 numbers to put into that pixel mask script for a different camera filter combination. And to do that, all you need is those transmission numbers for the transmission curves for that combination. All right. Well, thanks, guys. Thanks for listening.
Well, thank you. I want to stop the video real quick.
Okay.
Where's the record button?